In moving on to this next section, we're getting away from the previous section, which had series whose terms were always positive. Now we're going to be dealing with series whose terms can be negative. They don't have to be negative. They're not all negative necessarily. They're not always alternating. Sometimes they will be, like we saw from a geometric series with a common ratio that's negative. But in this section here, we're not going to be dealing with just terms whose always series whose terms are always positive. Now we're going to start with what I just referenced here a moment ago, an alternating series. So let's take a look at what an alternating series looks like, and let's put some words to it. An alternating series is a series whose terms are alternately positive and negative. Oops. So it might look something like this. We could have an a sub 1 minus a sub 2 plus a sub 3 minus a sub 4, and then just continuing that pattern, plus dot 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 plus. You'll see in alternating series usually a term like this. So a negative 1 to the n minus 1 times a sub n plus dot dot dot. That term, that negative 1 to the n minus 1, in this example, is what changes the sign of each new term. Okay, or it could start off with a negative. Instead of starting off with just a sub 1, it could be negative a sub 1 plus a sub 2 minus a sub 3 plus a sub 4 minus dot 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 plus, this time it'd be negative 1 to the n times a sub n plus dot dot dot. Now, in each of these examples here, we're going to require or have each term a sub k greater than 0 for every k. So in dealing with an alternating series, the sign that's associated with the term, we actually treat that as a separate entity, and we look at the term as just a magnitude. So in everything that we're going to be dealing with, the terms themselves are considered to be positive, and we're either adding or subtracting that term from the previous terms. So always keep that in mind, that we look at the terms as magnitudes. Okay. Well, we have a pretty straightforward test called the alternating series test that determines the convergence or divergence of an alternating series. The alternating series test. And I should make that look better. There we go. All right. An alternating series is convergent if the following two conditions are satisfied. And the two conditions are: 1, we need a sub k plus 1 less than a sub k for every k. Now hopefully you recognize what that's telling us. Since each new term, this is a new term, since each new term is less than the term right before it, that means the series is decreasing. Actually, it doesn't be strictly decreasing. It could be less than or equal to. So as long as, there's less than or equal to. So it's essentially decreasing. And the second is that the limit as n approaches infinity of a sub n is 0. So essentially what we need to have happen here is we need the terms of the series to be decreasing and approaching zero. If those two things are met, then the alternating series will converge. If either one of those is not true, then the alternating series will diverge. Let's take a look at a series that's close to one that we've already worked with. Call this example number 1. Does the alternating harmonic series converge? And there's a couple different versions of the alternating harmonic series. If you could start on the positive or start on the negative, and we're going to start on the positive. So we're going to use this version of it. All right, so, well, what do I need to show? Well, I need to show these two conditions up here are true for it to converge, or show one of them is false for it to diverge. Now, I tend, when I work on an alternating series, I tend to do number 2 first in that list. I tend to look at the limit as it approaches infinity of the terms. And the reason why I do that is the limit is usually easier to determine than whether the series is the terms of the sequence are decreasing. And so if I get this to be something other than 0, then I don't have to go worry about the other part of it. So that's why I tend to do this one first. Now remember, we are pulling out the magnitudes of the terms. So I'm ignoring the fact that it's alternating. So I'm just taking the limit as n approaches infinity of 1 over n. And obviously enough, I hope that that is equal to 0. Now, what about the decreasing part? Well, again, I'm looking at only magnitudes. I think it's fairly clear that n plus 1 is greater than or equal to n. And then if I take reciprocals of both sides, 1 over n plus 1 is going to be less than or equal to 1 over n for all n. But 1 over n plus 1, isn't that just a sub n plus 1? And isn't this just equal to a sub n? Well, now I've met number 1, and I've met number 2, and I've met number 1. Therefore, the alternating harmonic series is convergent. So this will have a little bit of a consequence later that we'll talk about. Alternating harmonic series. The fact that the harmonic series itself diverges, but the alternating harmonic series converges, is kind of a different thing, and it has a property that we'll talk about more later. I do want to take a look a little bit at, let me see if I can switch to a different. All right, my computer's acting a little bit on the slow side here for some strange reason, but I wanted to take a quick look at the harmonic series, the alternating harmonic series, and what I actually have on here also is the opposite of the harmonic series to see how things behave. Now I'm a few terms into this here. Let's see if I can get this working properly. Well, the harmonic series, of course, is 1 plus 1/2 plus 1/3 plus 1/4 and so forth on that line. So it's actually represented in blue, but it coincides. You'll see the green right here, this green dot. That's 1. That's the first term. It's the same for the alternating harmonic series, which are represented in green, so they overlap in the alternating harmonic series is second in the list, so it covers up the blue dot. But anyways, so we get 1 plus 1/2 makes 1.5, plus 1/3 makes whatever that makes, 1 plus 1/2 plus 1/3. So that's these 3 dots right here. Down over here in these orange dots, we have -1, minus a half, minus a third. So you'll see that mirror the harmonic series just across the x-axis. But the green dots here, so this is 1 minus a half plus a third. And then let's continue this a little bit here. And then we should have, everything's a little bit delayed on my computer at the moment. So, and then up here we have plus a fourth and then minus a fourth down here. But after that, 1 minus a half plus a third minus a fourth. And let's just keep this going. Hopefully we won't have much delay. Plus a fifth. Maybe I can just have this thing play itself out for me here. All right, let's stop right there. I apologize for the technological issue here, but you can see that the harmonic series just keeps growing up, or the opposite of the harmonic series just keeps growing down. But the alternating harmonic series, every other time, because I'm adding or subtracting, and I keep zeroing in over here. Well, why is that? I add 1, then I'm going to subtract a half. That half was smaller than the one that I added. Then I'm going to add a third, which was smaller than the half I just subtracted. Then I'm going to subtract a fourth, which was smaller than the third I had just added, and so forth. Every other amount, every new term is smaller than the previous one, so the amount I add or subtract was less than I moved before, and the graph just seems to be zeroing in on a value down over here, where the harmonic series, or its opposite, just keep growing off to infinity rather slowly, but they do keep growing off to infinity. So hopefully that kind of illustrates what's going on with this harmonic series and why the alternating harmonic series converges even though the harmonic series itself diverges. Let's see here. Again, I'm going to have a little bit of a delay with my computer, I guess, as I go through this, but it's okay. Example number 2, does the series converge? Okay, so let's see. In part A, we have the sum from n equals 1 to infinity, -1 to the power of n minus 1, 2 to the n divided by 4n squared minus 3 in the denominator. And then for part B, it's the sum from n equals 1 to infinity, -1 to the n minus 1. And then we're going to have 4. These things, you should be sticking to the algorithm that I've been teaching you for determining whether a series converges or diverges. Do you identify it as a certain type? Well, now our types include the alternating series. That's a type, and we have a way of handling it. So before it was geometric and telescoping as our only, and harmonic as our two types. Actually, that's not true. We're thinking of the section that we're in. We actually do a p-series also. So we have the geometric series, the p-series, harmonic, which is also a p-series, telescoping series, and now we also have the alternating series as one of our types. Okay, so since these have that term here on both of them, that tells us that the terms are going to be alternating, so we can try the alternating series test to determine whether or not the series converges. You should pause the video and go see if you can work that out on your own before watching how I do it. All right, so like I said, I always try the limit first because I want to make sure the limit is going to 0, because if it's not, I know the series will diverge. Also remember that I said we're going to be looking at the magnitude of the terms. We don't in looking at the limit, we don't look at the negatives here. Now, because we have an quadratic on the bottom, a quadratic on the bottom, and linear on the top. We know the quadratic is going to grow faster than the linear, and we should know that this goes to 0. So that's good because we know that meets one of our criteria. If you need to show more detail, you can divide by the highest power of n or apply L'Hopital's rule or something to work that out. But we should all know that that goes on to 0. Now, to show that the series is decreasing, we could use calculus, or we could use the definition of decreasing, similar to what we did in this example way up at the top. But I don't want to do that. So I'm going to use some calculus for this. So let's let f of x be equal to 2 to the x divided by 4x squared minus 3. So I need the derivative to be negative from 1 to infinity, or at least at some point to infinity. Maybe there was a few terms where it doesn't behave that way, but going off to infinity. All right, so let's apply our quotient rule low here. 4x squared minus 3 d high minus high d low, all that good stuff, over low squared. Now, typically what we want to do here at this point, if we were doing all the rigorous calculus that we would need, is we want to figure out where this is undefined, where this is equal to 0, and set up our intervals, and then run some tests. But I'm going to be a little more clever than that, I hope. And I'm going to do a little bit of factoring here and see about rewriting this. Actually, no, let's not factor. Let's just multiply some things together, because notice that if I distribute here, I'm going to end up with a negative 8. I'm sorry, just a positive 8x squared. And then I get minus 16x squared from this over here. And that comes out to be a negative 8x squared. And then a minus 6 when I distribute the 2 to the 3. And then that's over 4x squared minus 3 quantity squared. Now, again, if you're thinking cleverly about this, and I factor out that negative, this expression here is going to be less than 0, always. The term in the parentheses at the top, this stuff up here, that stuff up there, that's a, x squared non-negative times 8, still non-negative, add 6, has to be positive, and then you're going to take the opposite of it. It's going to be negative. The denominator is raised to the second power. That's always going to be positive, or at least non-negative. And so that negative divided by the positive is going to be less than 0. So the series is decreasing, and therefore the series is going to converge. Therefore, let's see. I guess it should be a little bit more complete. The series is decreasing. And so by the alternating series test, this series converges. All right, now part B. Again, if you haven't tried part B, you should pause the video and go try part B. But like I said, I'm going to jump right into looking at the limit as n approaches infinity. And this time it's 2 to the n over 4n minus 3. And that limit works out to be just 2 over 4, or 1/2. 1/2 is not 0. So the series diverges. So this alternating series diverges.